Okay, let's try to wrap up chapter 9 here, and this will be a wrap on Chem 151 as well. The last topic that I want to address from chapter 9 is called molecular orbital theory. And the idea here is this is sort of an alternative version of developing an understanding of bonding and what's happening between the atoms in a molecule, different from drawing a Lewis structure to evaluate the bonding. And it turns out this is a little more sophisticated, and there are certain situations where this gives us an answer for describing bonding that matches more appropriately with observed experimental considerations. And one example, and it's a little more complicated than I think is necessary to go into in the structures we're going to try to draw here for this part of the lecture. But a good example is just oxygen, the O2 molecule. If we draw the Lewis structure and follow the rules for Lewis structures, we end up with all the electrons paired. And that doesn't match the reality of molecular oxygen. If you condense oxygen into a liquid, it actually interacts with a magnetic field, which is an indication of unpaired electrons. So the oxygen molecule actually has unpaired electrons in it. If you do a molecular orbital treatment and imagine the atomic orbitals on the oxygen atoms combining together to form molecular orbitals, and then you fill the valence electrons into those molecular orbitals, you actually reach a point where you have two molecular orbitals of the same energy, and you put one electron into each of them, and your structure does have two unpaired electrons. So as you progress into chemistry, right, molecular orbital theory becomes a fairly important idea. Particularly those of you who go on to organic chemistry, you'll get a reintroduction to this at the beginning of your organic chemistry class. And that's part of the reason why I don't feel like we should go too deep into molecular orbital theory. It really is not going to come up in anything we'll talk about in Chem 152 or Chem 2 for us at Craven Community College. And if you do go on to organic chemistry, I feel like it's kind of understood that it's been a while since people have heard about molecular orbital theory. I know when I teach the organic class at Craven, right, we'll go back over the ideas that I'm going to talk about here and then expand on them into specific issues for organic chemistry. Now, that said, I think you should have a kind of a basic understanding of what is happening here. So if we go back to just atomic orbitals, we mentioned in chapter 7, every atom has a set of orbitals that are filled. Some of those orbitals are kind of spherical. So that little thing is my attempt to make that a three-dimensional shape. So if we think about, and let's use carbon as our example. Carbon has one s orbital that's filled with electrons. That would be a core electron, a core set of electrons, though not involved in bonding. But then it has the 2s sublevel that is filled, and the 2p sublevel is partially filled. So for carbon, the atomic orbitals that are relevant to bonding are the 2s orbital, and then the set of 2p orbitals. And remember that p orbitals are directional. So there's one along the z-axis, so let's call that one p sub z. There's one along the x-axis, and yeah, if I call that x, so that would be the 2px. That would mean the y is kind of in and out of the paper. So there's a lobe of the y that is kind of behind the paper, and a lobe of the y that is out in front of the paper. Kind of like that. So the y is kind of going like this, and my drawing ability may not be the greatest there. And I put the open lobe back to make sure I have a right-hand coordinate. That's the kind of weird movement I was doing there, making sure I have a right-handed coordinate system for my XYZ coordinates. The p orbitals have different shading here to apply different sign for the evaluation of the electron density. There's a kind of a positive lobe and a negative lobe, and that comes into play when we do think about combining orbitals, and that's what I particularly want to mention here. If we are combining carbon atoms to make, say, carbon-carbon bonds, right, many of these orbitals may be able to interact in that attempt to describe the orbitals that are producing the bonds we see in a carbon molecule. Okay, and that's what I do want to discuss here. So let's back up a second. All right, carbon is, I think, helpful because it has all the orbitals. Hydrogen doesn't show us the p orbitals, and I do think we want to think about what happens with the p orbitals. But let's think about hydrogen. So we know hydrogen makes a diatomic molecule, but hydrogen will be a lot simpler for us to think about here at first because it just has the s orbital. But if we think about two hydrogen atoms, they're separated here, so they have not gotten close enough to form a bond yet. Each one has one electron in its 1s orbital. And what we want to think about is, what if I take that 1s orbital, that spherical shape, but as I bring these molecules closer together, those two orbitals start to interact with each other, right? And that's kind of the key here, is how will the waves that describe where these electrons are combine together to make a new orbital that is stretched across the entire molecule. And for hydrogen, since they're just both spheres, this is a little easier to visualize. There's two possibilities here. One is constructive interference between the waves, and that would kind of be the waves fusing together. That constructive interference will be lower in energy. So if each of these hydrogens is at a certain energy with their one spin-up electron, if we combine those two orbitals together, we would get a picture that looks kind of like this. So the dots here would represent the hydrogen atoms once they're closer together. But if those two waves kind of fuse together, we get an orbital that kind of looks like those two orbitals, but now it's joined together. So it almost looks like a peanut, sort of. But there's electron density in between the hydrogen atoms, and that is what we could imagine as holding the bond together. Now, if we get constructive interference, we can also get destructive interference. And if one of these areas of electron density starts to destroy the other one, right, instead of adding these together, it's almost like we're subtracting them. That would give us another picture here. This would be much higher in energy, but what would happen here is the orbitals would destroy each other in the middle, in between, but there'd be some left over on the side. So on this side, we'd have a little bit of that lobe of the molecular orbital, and then on this side, we would have an orbital of another sign. Now, basically what I did here, to imagine the destructive interference, you can think about subtracting. So if this one's positive and this one's positive, you add them together, they add together. But if they're both positive, you take one and you add the negative of the other one. That's almost like subtracting. So visually, what I did is I just imagined one as a circle and the other one as a circle with the opposite sign. And when you add those together, they're going to cancel out where they overlap, but there'll still be a little bit left on the edges. That's a good way to think about destructive interference. Now, this is lower in energy, this is higher in energy. Both of the electrons will end up down here, right? And that would change the spin. One would now have to be spin down, right? But this is part of what we can imagine as the driving force for why the bond between two hydrogen atoms forms, because the electrons get to move to a position of lower energy. And if the electrons are living in this molecular orbital, that helps hold them together. Now, if you did have enough electrons that they would have to go up here, populating electrons here would drive the two atoms apart, because where the electrons are living is not helping hold them together, and they would just push the molecule apart. And this is why you don't see, for instance, He2 or a diatomic helium molecule, because if you try to put two heliums together and you had 4 electrons, it would fill both of these orbitals. That would be no net bonding between the heliums. They wouldn't stay together. They'd continue to float apart. Okay, so that's kind of the basic idea of what is happening with molecular orbitals. And then the other thing that I really want to point out is going to relate particularly to p orbitals. So the other thing, well, actually, let me say here, this is called a bonding orbital, where the electron density is between the atoms. And if the bonding occurs between the two atoms, like along the internuclear axis, this is called a sigma bond. And the Greek letter looks like that, so sigma bond. When the orbital looks like this and there's no electron density between the atoms, this is called an antibonding orbital. And since it is sigma, it is along the internuclear axis. That was a bad attempt at a sigma. This is called a sigma star. The little star means anti-bonding or not leading to bonding. Okay. Now, it looks like I went a little longer than I thought. I think I'm going to have to pause the video. We will then, I guess, have a second video on molecular orbital theory because I want to talk about the other possibilities of carbon and how we can have more than a single bond for carbon. We can have single bonds, double bonds, triple bonds. That's a function of the way those orbitals interact. That'll be an appropriate thing for us to talk about as sort of just a basis of molecular orbital theory. So despite my previous promise, there'll be one more additional video from Chapter 9.